Thank you everyone for coming here. It is really great to be back. And it's been more than 2 years, I can't believe it. But it is on the books. I know that I'm on my 3rd year in the postdoc. This time I'm in Austrian Academy of Sciences. But this research actually started in the Research Institute for Symbolic Computation in Johannes Kepler University. Also in Linz, also at the same location. But I recently moved to this institute, Johann Reuter Institute for Computational and Applied Mathematics, and I'm in the Symbolic Computation group of that. So, and I know this, when it comes to Q-series, this is the house of Maple packages. We have Frank Garden, who has written the Q-series package. He's waving at me, I guess. But RISC is an institute which is known for a lot of great research and a lot of great mathematical packages, especially when it comes to symbolic computation and proving things automatically. And we wanted to just add with Jakob, we wanted to add something that would benefit my research, the other research that is around what I like to do. So we have included some functionality both on the experimental side and on the symbolic side. So for that, I need to start defining some objects to give you a good demonstration, hopefully a good demonstration of the software package that is about to be published, that is about to be available to everyone in the next month. It is already, it's just in the documentation phase. All right, the first thing first, partitions. That is how I segue to Q-series. A partition pi is a finite sequence of non-increasing positive integers with parts written in that format. And it has so many terms, you can sum it up. The total sum, I call it the norm, you can call it the size. We usually just say that's the size of that with absolute values of pi. And here are a couple of examples. 511, it is a finite sequence that is non-increasing. There can be repetitions like the ones here. And when you add the terms, it is a partition of 7. It adds up to 7. It is a partition of 7. And the empty sequence, empty list, is the unique partition of 0. It is still a finite sequence for what? For what we know. All right. With that, we want to count these objects. We want to find identities about these objects and play with that. And this is a really combinatorial object. One thing that you can do is you can work with these objects one by one, do direct combinatorials on them, or you can just move on to generating functions and try to work with them in bulk. And for that, I should define the generating functions. And for me, it's just a formal definition. Given a sequence an, you take it an to qn, make a series, and that is the generating function for that sequence an. Whatever those ans might count, whatever those ans might be. And let's u be the set of all the partitions. Here's one example of a generating function. You take your partitions, you group them with respect to their sizes. You just take your sequences, add them up their sizes, and then you can just say, okay, this is a sequence of number of partitions of something. That's a generating function. And you can start listing it. So for q to the power 0, you have one partition of 0, which was the empty sequence. For q to the power 1, you have one partition of 1. For 2, you have two partitions of 2, so on and so forth. Then the question becomes, can we write the generating function as a closed formula? Can we write it in different ways? Can we find identities? And for that, we need to define some objects. And I think you're going to like this. We were talking about just a second ago. One of those objects is the qPokehammer symbol. And this aq sub l is the qPokehammer symbol. That is a finite product. Starts with 1 minus a and goes all the way to 1 minus aq, 1 minus aq squared. It is just the q analog of factorial, with give or take a term. And aq infinity is that limit l goes to infinity. Here's this condition, but it converts to formal series ring 2, so you can just drop it if you don't want that. That's totally fine for us. If you have too many of these qPokehammer symbols with the same base, with the same number of multiplications, it is usually helpful to just combine them and abuse the notation a tiny bit. So a1, a2, a to the k sub q sub base q sub l. I'm just going to take it as the product of qPokehammers. Okay? And what are they good for? They are basically the building blocks when it comes to the partition theory. Here's one example. The product 1 over qn is the generating function for the number of partitions with parts less than or equal to n. So you start with 1, you go all the way to n, one step at a time. And with this reciprocal, it becomes the generating function for a number of partitions with parts all less than or equal to n, parts may repeat. Or this is the same thing as it is the generating function for the number of partitions with number of parts less than or equal to n. So you have multiple representations of something. Or another example is, if you don't have a reciprocal, but if you have a negative, minus q sub n is the generating function for the number of partitions into distinct parts less than or equal to n. This time I'm not going to have that switch, I'm not going to be able to do it. But let's move on to another more complicated example, so to say. This one, 1 over q squared q5 sub infinity is the generating function for partitions in part 2 mod 5. So I start with a 2, then my steps are of size 5. So all the parts that I'm going to get are 2, 7, 12, 17, so on and so forth. And this infinity drops that bound, whatever that might be. Right? So this is how we build these objects. And with epoch hammer and with that bound on the multiplication, how many multiplications you want to have, you can actually put one bound. But then you can just move on to the q binomials, and then you have two bounds. So it is defined this way, so m plus n sub q, m plus n choose n sub q is given by this epoch hammer symbol, if m and n are all positive. And this is the generating function, if you interpret that, is the generating function for a number of partitions that fits in an m by n box. So you have two bounds. So these are all good, useful objects that are in the core of partition theory, that are in the core of Q series 2. Right? So now that we have the objects, let's move on to what I am interested in. Let's move more particular to partition identities. And for that, I want to just show you one identity. And we're not going to go deeply into that. But the point is, there is a type of identity in partition theory called gap congruence identity. There are two sets completed from different two spaces. On one, you're counting partitions with some gap condition that you impose. And on the other hand, you are counting partitions with some congruence condition that you impose. And if you're lucky, you say that these numbers that you count are the same. So the Rogers-Lamontville identity, there are two of them. The first one, with n equals 1, you count the number of partitions where the parts of the partition, where the gaps between parts is larger than or equal to 2. You count these partitions for, let's say, partitions of 15. The number of these partitions is the same, is equal to the number of partitions into parts 1 or 4 mod 5. So on one side, you're counting partitions where all the parts differ by at least 2, maybe differ by 10. You don't care about that. But on the other side, you're counting partitions with congruence conditions, where the parts are 1 or 4 mod 5, and they can repeat. You don't even have a gap condition. And turns out this combinatorial identity exists. These two sets are equanimous. This is the combinatorial side of things. This is the gap condition is equal to a congruence condition. The analytic version of that is a sum is equal to product identity. So you have a sum that represents, theoretically, if you can interpret it that way, that represents your gap condition generally. And it is equal to a product that represents your congruence condition, if you can interpret that combinatorially. So there is this 4 objects. There's an analytic version, sum is equal to product identity. There is this combinatorial identity, which is gap is equal to congruence. So any switch between these can be used to prove one of these identities. If you can show that the generating function for number of partitions with these gaps turns out to be that product, it would also be proving this identity. So these type of switches are really important for us. And there are not that many tools, or there are not that many things that we know about these identities. We don't know where to find them. Whenever we find one that is miraculous, we don't know how to prove them when we find one. And it is usually a unique proof that a technique can be applied, but technique is always a little bit different here and there. So for that, I kind of begged my now co-author Jakob Ablinger to help me put together a package where we can experiment some, where we can symbolically add some tools that helps with this transition, and that's how this qFunctions Mathematica package started. The first thing, let's start with q difference equations. we had the generating function with q. Let's say we have another variable in it. So we have q to the nth, but let's say we have another variable y to the n. And if you can find the polynomial relation of this fyq generating function that satisfies some polynomial relation which shifts in this y, q shifts, we will call these type of polynomial relations to be q difference equations. There's also the q differential equations, and this is equivalent to recurrences for the coefficients. All of these things are pretty much equivalent, but the q difference equation seems to be working really well when it comes to q series, especially coming from partition theory side. And one example is, if you look at the sum that appears in Rajasthan partitions, you can just say, if you take along the y to the n, that is m equals 1 case of that, it satisfies a functional equation of this sort, where you have q shifts in y, and polynomial coefficients in y and q. Okay? And this is actually natural. So when you look at the Rajasthan identity, that term, that yn that we tagged along, is the number of partitions, number of parts in that partition that you count. So sometimes it actually appears naturally. What tag you should use sometimes acts naturally, so that you can try to find a q shift equation, q difference equation, using this natural tag. But not necessarily at all times this is going to be natural, or not necessarily at all times we know what statistic, what new variable that we should take along to get a q difference equation, which I will start calling it q shift equation from now on, to separate from differential equation part. We don't know what to tag along for the most case when it comes to a q shift equation. And two, even if you get lucky and tag along the correct thing, how would you find the q shift equation? So that's the first thing that we have added to the qFunctions package. You can experimentally try to find these q shift equations. Let me show you a more complicated example. This was just one sum and a yn. So if you can just find a q shift equation, it is almost equal with the recurrences. You're getting rid of one sum. If you look at the Cabreri's theorem, the analytic version of the Cabreri's theorem that is used Canada and Russell, they found it using computer search. And we have proven this directly with Professor Barkovich in two different ways. Three different ways. Now three, or are you certain?
No, that's going to be the way number 4.
Okay, apparently we have already proven it in 3 different ways. I thought it was 2, I was wrong. And now I actually have a new proof of that, so it's going to be 4 different ways. So which,
You didn't believe it to start with?
which statistic would you take along? The point is, the most natural statistic is to have the number of parts again, which is y to the power 2n plus n. And you can try to search for a q shift equation, which I will do in a second. But if you look at that natural statistic, you will fail. But this package, we're hoping, is going to help us to create more experimental q shift equations to find them. And there are so many different Mathematica implementations that can prove, once you find one of these things, that can prove these q shift equations later on. So maybe I should move on that. Yeah, we can get the other statistics too. So let's move on Mathematica. All right, so qFunctions package, and I'm just...
Pull you back just a bit.
Please.
So it sounds like I want to think of this Q shift as you're saying, like, introduce some natural statistic, and then you would hope that you get some sort of bivariant recurrence that you don't really see when you don't have the statistic.
You're completely right. Exactly.
That's what you want me to think.
So that natural. Sometimes unnatural is more natural than natural.
Okay.
So the identity appears, the identity that is suggested, or identity that is found, which is again miraculous how this identity came about.
Mm-hmm.
It appears when that statistic goes to 1, when y is 1, when x is 1, whatever that might be. But the point is, when you're searching for a proof, you need a tag to be able to have a functional equation and modify this object to show that this dough, when you massage it, turns into this bread.
Yep.
And the point is, not every time the natural statistic works, and sometimes, as Professor Berkovich said, the unnatural statistic might be more natural, and it can give us better solutions. Okay, so before we go to method of matrix, so here I just started the Mathematica package. I'm just initiating the qFunctions package, and it's saying that I should also be adding the holonomic functions, which belongs to Christoph Kuchan. It is in the RISC ergo sum. It is a great package. It can do a lot of things. If you find a recurrence, you can prove it with that in Q level or in Q equals 1 case. You can search for recurrences of sums in Q equals 1 case. You can search for recurrences of summands in Q case or Q equals 1 case. It is a great package. All along, really strong package from Christoph Kuchan. And I want to add another package. This is Carsten Schneider's Sigma package, which I have been working on a little bit more. It is also a great package. It gives an error with creative telescoping, but it says I'm having trouble with holonomic functions. Nothing to do with us. In Sigma, you can also find recurrences. You can also solve recurrences. And it's an all-in-all great package. And both of these are symbolic computation packages. So when you find something, you can say, how did you find that? Can you give me a certificate? And it will tell you the steps that you need to do by hand to verify that. So anything that you get actually with modulo in a poll that they might oversee is proven. All right, let's look at the Q-shift equations. So we looked at the Rajasthan-Monjan example. So I'm taking a sum, Q to the n squared divided by Q sub n, the Pokemer, and I'm taking it with this yn. And I'm just taking the first 30 summands, and I will print the 5. So it looks like that. The first 5 summands are like that. I'm just checking if using this data, if I can find a Q-shift equation, if I can guess a Q-shift equation, with 2 shifts, the order of shifts is 2, and where the variables, the polynomial variables are also going to 2. Maybe I should change the size of the cluster. Okay. Yeah, so I can just check, can you search for a Q-shift equation? Can you find something? And it says more restrictions are needed. One of the things that you can do is the expansion. You can set the expansion to be higher. You can get more series terms and check more variables. But I have found something for you. So it finds something with 3 free variables, C1, C2, and C3. One thing that you can do with that is you can take this term and say, what if all the C's are 0? That is one guess anyway. We're not proving anything. We're just guessing a Q-shift equation at the moment. And if you look at this guess, it is equivalent to the guess that we have. And when I'm looking at Q-shift equations, when I'm looking at Q recurrences, everything is set equal to 0. So this is equal to 0 is what I have. It is just to reduce redundancy, that we're not writing equals. Another way so now that we have seen there are a lot of free variables, one thing that you can do is you can try to drop terms, drop the recurrences order, drop the order of the polynomial coefficients, and try to hunt down for a single Q-shift equation. So I drop the polynomial degrees of y and q. So if I do that, I directly get what was known for the Rajasthan-Monjan case, right? Or another one is, so this is helpful in some cases. You can make an assumption. You can say on the highest shift, on the highest degree term, I want to see that 1 minus yq. Whatever that term would mean, it's just going to give us an iteration of the minimal shift equation. But you can just force our guesser to have that for you. Okay, let's look at the comparative example, the more complicated one.
So wait a second, the last one, was it already proven?
This one?
Because, yeah, is it proven or you just still guess?
Well, these are all guesses, we can easily prove that, but this is equivalent to the one that is known, so we can consider that to be proven. But the package, for the guesser, it is an experimental thing. It is not guessing it. If you want to prove it, you can use sigma, you can use holonomic functions, you can use Q multisum. There are a lot of packages from RISC that can prove these
easily. This is more about conjecture.
Exactly. I get stuck all the time, especially when it comes to having these type of identities. So this is a way of just saying, what is the next step? Can I make a guess so that maybe I can try to work on that number? So let's look at the Caparelli one, which has two sums in n and m. And here I'm writing the same thing, but directly inside of my function. So I'm summing n and m to 20. I put the natural statistic, x to the power 2n plus m, which is the number of parts. I am saying the shifts that we want to see can go all the way to order 3. And the shifts in the polynomial degrees in x should go to 3, polynomial degrees in q should go all the way to 20. And I want these series to be opened up till threshold q to the power big O 101. Big O q to the power 101. So I want to have a lot of terms. I want to guess this with the natural statistic. It doesn't take long. It says no solution because the natural statistic doesn't always work. But if I were to have this unnatural statistic, 3n plus 2m combinatorially means nothing to me, but it's a 3n plus 2m. And if I were to do all the same things, except I'm even keeping my q degree so low, I'm able to guess something. This is a guess at the moment, but this can be proven really easily. Yes?
What was your original statistic 2n plus m?
Yes, and there is the number of parts in a partition.
Yeah.
That satisfies Caparelli's gap conditions.
So how are you linked to the 3m plus 2m?
A lot of trial.
Okay.
And the point is to experiment with this package, this portion of the package. So you can just create a for loop, try all of them.
Okay.
Yeah, exactly. But once you find it, it is a piece of cake to prove it. Because this is equivalent to a recurrence, and let me show you. I have the shift equation, right? And that is, if I were to write this as a sum of polynomials in Q, x to the n, that is equivalent to a recurrence in these coefficients. And here is the recurrence for the coefficients. And I can directly do this formal switch. That's totally fine. It's included in the package. I'm just going from a Q shift equation to Q recurrence. And then once you see these type of switches, you can try to manipulate this shift equation of this recurrence to reduce the degrees of the recurrences. Let's look at this one. I see that the shift equation on the top has this 1 minus q squared x term. So one thing is that maybe we can divide everything with a q polymer x q infinity. How did I make this change? How did I make this choice? Experimental again. You can choose whatever you like. All the substitutions, you can do it formally. I guess this, I want to take my f of x with that shift equation. I want to divide all my f of x's with x q sub infinity. And it gives me a new shift equation, which is equivalent. And this is equal to 0, so I can only get the numerator of that. That is clear for us, right? I can just clear the denominators. I can take this thing, this term, take the whole thing all together, take the numerator of that, because it's equal to 0, and combine all the f's, and then I'm changing the name. This is a new function now, so I'm changing it to g. I have a new shift equation that I derived from this experimental f. And now let's look at the recurrence equivalent of this. The recurrence equivalent of that for the new coefficient e has 1 degree less. I start with an order 3 recurrence. I did one switch. I end up with an order 2 recurrence, thanks to that substitution that I did in the middle. So we can play this game. Now we can do substitution at the recurrence level, go back to the shift equation, try to do a substitution at that level, go back, and try to find an expression for one of these coefficients or one of those functions. Once you did that, you just go back. That's one proof. If you don't want to do it, once you're at the guess level, write your function explicitly, put it in sigma, it will give you the proof. There are many different ways that you can prove it. This method, this guess, then go, shift, go, recurse, go, shift, go, recurse, doing substitutions, are actually how Katrin Brinkman, Christian Schaefer, and our former student, Christian Schaefer, and Karl Malmberg recently proved 7 of 21 Canada-Russell conjectures. Now 9 of them are proven, as far as I know. But this method of experimental finding something, then switching to the point where you can guess it and go back, is how they proved these identities. Okay.
Is it possible to reduce the order of the last recurrence further?
Maybe. I don't think so, but
Right.
I did. But we solved this anyway, so it's okay. That will be the fourth proof of copy-release, hopefully coming soon. All right, let's go back to the presentation and let's talk about the weighted verse. So method of weighted verse. This is dear to my heart for two reasons. One, it was introduced by Basil Gordon and Professor Allabi that is sitting in the audience. And two, I tried to learn this method and I failed. This happened before. It was such a natural method, but there's a matrix involved. I kept on forgetting what that meant. So this is a really basic method. Now that I know it, I can say it's basic. And you start this way. You want to handle gap conditions, so you abstractify your gap conditions. You find an abstract version of the gap conditions. So for that, you start with an alphabet. I will start with A, B, and C. Let's say I start with an alphabet that is in a particular order. A is less than B, that is less than C. So with that, you also introduce levels. So there's the introduced order A, B, C, and there's the natural order. So there's A1, B1, C1, A2, B2, C2. So you have levels of these orders, levels of these objects. And once you have an abstract version of natural numbers, maybe this you can easily identify this with 1, 2, 3, 4, 5, 6, all of that, just changing variables directly. Once you have the abstract version of that, you can start imposing bounds. You can start imposing gap conditions, such as this one. You can say if Bn appears in your partition, if you pick up Bn in any level, do not pick up an An. Or if Bn appears, do not pick up an An, but An minus 1 is okay. That is just a gap condition, right? You can create these abstract gap conditions, and you can have it for every combination. Bn to An, Bn to Cn, An to Bn, An to An itself. So you have all these conditions, and that creates a gap matrix. And nowadays we read this as from to. So from A, if you want to go to another B, you need to go one level down. That one represents that you need to go one level down. If you want to go to a C, you need to go one level down. But if you want to go from a C, let's say you're at the 4th level C, if you want to go to a D, you can stay in 4th level. You just need to go 0 level. So you had a C4, you can follow it up with a B4. Okay? So this is the abstract version of the gap conditions, and you encode all of the gap conditions that you have with a matrix. Then you can just say, okay, can I write the generating functions that satisfy these gap conditions, where my largest part is a 5b or a b5, or my largest part is a cn or an an at some level. And with the gap conditions, we should be able to do that and go down. And this is where we derive from the original method. The original method was that we had the gap condition, we knew that, we suggest the generating function that was already found, and showed that it satisfies the gap conditions, it goes to the product. And here we move on to Jean Douce's technique, but we want to write these recurrences. And we should be able to do that symbolically. Once you're given a gap matrix, you can find these recurrences symbolically, where your largest part is Cn, Bn, An, whatever, and then you can try to solve it using solvers. So, yeah, the task is to find generating functions for these type of partitions, and you just need to write the recurrences where you set your largest part and then backtrace what the second largest part can be, what the third largest part can be, and so on and so forth. So let's move on to directly that. Here's a toy example, that 1, 1, 1, 1, 1, 1, 1, 0, 0 matrix with the order A, B, and C. I did something wrong, and now we're waiting on Mathematica. I didn't do something, so okay, very good. So let's say I want to write the recurrences as functions being in Gn. No, it can be done formally. And this is symbolic, so you can just take it as a proof. However you will do it by hand, we are doing it the same way in the function 2. So here's a coupled system. This is saying if you're in the nth level of A, if your largest part was an, you need to go cn minus 1, or you need to go cn minus 1 with this vector. The second one says if you're at the bn, you need to take these values, and so on and so forth. This gives us a coupled system. Coupled system of recurrences for all these generating functions. This is where the holonomic functions comes into play. You can uncouple this system. You can just say, take my recurrence system, please. Can you uncouple it for GA, GB, and GC? That is the holonomic functions. And if you look at it, these are just order 1 recurrences. So technically, we're already done. The last one, as an example, it is GC of n. It only depends with GC of n plus 1, right? Or even for more complicated cases, you can set your recurrence. I took the third recurrence, the last one, and set it equal to 0. And you can say, you can ask sigma, Carsten-Schneider sigma, to say, can you find a solution for me? And if you're lucky, you will get a solution directly. You have a particular solution, which is 0, or you have a general solution for the homogeneous system, and that is that product. And from this abstract value set to normal natural numbers, you can just drop it down with some number of variable changes. And here it is. You would end up with this product. Okay, so with that, with the system of recurrences, you can just get that, okay, the partitions that satisfy these gap conditions have the generating function that. So we were on the gap condition side, we were on the sum side, we were handling that abstractly, and we ended up in a product side, which is on the concrete side. So this method can be used in this switch. And now we have this method encoded, so we can experiment a lot. And we can hopefully find new identities using this method, or prove new identities using this method.
So Alif, what is this upper bound on the J in the product, n? What's that? This. Yeah.
It should be an infinity if I set that limit to infinity, but I believe this is CG sub Cn, so that was that n. That I decided to take the bound later on to infinity, but forgot to change it there. Yeah, thank you. Thank you for catching that. Yeah, so, all right. We can do a lot more. I will talk about this method much more in the number theory seminar in 8 days. Please feel free to show up. I will prove Schur's identity. I will prove over partitions have the generating function that we know. And moreover, we already are using a new version of the weighted words method. But even more so, we have extended the weighted words method. Now, if you were to look at the first statement that we said, you need to start with an order where you have A is less than B less than C, and so on and so forth. You don't need to have them anymore. In the extension of the method, you don't even need to put an order here. You can get more combinatorial results just by a more general setup. And I should maybe explain it here. Oh, yeah, the most important bit is you can give it you can give R package any matrix that you like. If it doesn't merge, it will tell you. So it terminates at any case. In this case, it says the given condition matrix either does not yield a finite order recurrence, which is the case here, or the difference conditions are not consistent, are inconsistent. So that can mean that you weren't supposed to have an AN with a BN, but through a backdoor you can have it, and then it is not allowed. So we can identify all of these issues that we can exclude the matrices that we cannot do anything with, or which doesn't make sense. All right, let's move towards the last bit of it. All right. So cylindric partition. This is a general set. Introduced by Gessel and Christian Krabbenholder. Cylindric partition is given by this definition, whatever it might mean. It is a list of partitions, and there's a relation between these partitions. But that relation is given by a composition, a finite list, not necessarily a partition, and that thing is called a profile. And the point is, yeah, so we have a vector partition, we have a vector of partitions which satisfies a relation. With that, you can define a two-variable generating function where this size of the partition, size of the cylindrical partition means the sum of all the partition sizes, and the maximum means the maximum value of all the partitions, the top maximum value of all the partitions. And with that, apparently Borodin in 2007 said if you were to put that y to be 1, it is a product. So this is how music to my ears. Because it says if you can find what this is supposed to be, if you can find a representation, if you find a formula for f, when you plug it in y equals 1, it is going to be a product. That one is already given. More music to my ears came from Sylvie Cortiel and Thomas Welch. They made a simple substitution, just as we did before. They are multiplying the fyq function with a yqq sub infinity, and then say that this g function with a given profile satisfies a recurrence, a q-shift recurrence. This q should be downstairs. And the switch that is defined by J is a really simple switch. This should also be given to Sylvie Cortiel and Thomas Welch. There is another alternate. So this is some open formula that we can write. So we have included that in our package 2 to the point that given any profile that you pick, we can find the recurrences for that. And we know at y equals 1 it should be a product. So why not work on the recurrence side as much as we can? All right. So you can take any profile that you like. I take the 3, 0 profile here. I want to write my functions named to be g, and I want my functions in y and q. So you get your functional equation, that's q shift equation that this function satisfies. That's automatic. Or you take this 2, 1 profile, and you can directly automatically get that. Or if you don't want to deal with one by one, you can just say, please give me the whole system, where I have my functions to be named g. I have 2 parts in my profiles, and the parts add up to 3, and then it gives you all the system. So it gives the first one, second one. If there are more terms, it will give you the whole system. And now, again, we have an uncoupled system of q-shift equations. We know that we can switch from shift equations to recurrences. There is going to be an uncoupled system. We can, there's a coupled system. I have a coupled system. We can switch to recurrences. We can uncouple that. We can try to find these functions. And here, yeah, you can list the functions. There are auxiliary functions like that. Yeah, so I have this functional system. I can move to the recurrences directly for the coefficients of these functions. I can uncouple these things. So as you can see, this is g21 at n, depending on only g21 at n plus 1. So it's a recurrence of order 1. We already solved it. Or g30 of n plus 1, g30 of n plus 2. And the funny thing is, if you look at these coefficients carefully, we have actually proved the Rajushaman identity. Here is just the writing in some terms, but it is not so important. We have just proven the Rajushaman theorem coming from this cylindric partition side. And you can also check the Borodin product, the one that Borodin said, and you can also print what the product you were expecting at the end. Let's look at a more complicated example so that maybe we can just get something more. I want to look at all the profiles into 2 terms where they add up to 4. Here's a system of 3 functions. You can carry that to recurrences. You can uncouple this system. Now the recurrences are order 2, so it is not so easy. You can ask Carsten Schneider's sigma to say, do you have a solution, please? And it would say, go fish. It was just say, the only thing that I know is 0. Not this time. Then you can start playing with that. We have all the tools. You have the Q recurrence equation, the first recurrence equation here. You can just say, okay, at -1, y to the power -1 is going to be 0. I'm not going to have any coefficients. Y to the power 0 is going to be just 1. let me list some terms. So your series looks like this. I know this is going to be a product at the end, but the series side that we don't know, the terms look like this. So it seems like we have a Pokemon that is in the denominator. It looks like q squared something. Everything is going in powers of 2. So maybe I should take that and just divide it with, I'm apparently dividing it with the sigma's q Pokemon, but I can just change it with q Pokemon of ours too. So I just cut off these q factors, q4, q9. I saw that it's a q to the n squared. Or these Pokemons, we can multiply it out to see what the polynomial is. And then, the great thing is, yeah, you can again guess a recurrence. You can say, okay, I have polynomials, can you please find a recurrence? Is that possible? Right? This portion is experimental. All the way here, it was symbolic. This portion was just experimental. And we saw that there is a recurrence with an extra variable, a free variable, so we can just simplify that. So it says whatever is left on the inside seems to be satisfying this recurrence. Can you find a solution to that? So using tools, you can come to a point where you can look at the literature, or where you can try to solve the recurrence yourself. So again, you can go to q-shift equation, try to modify it, try to drop the degree. Sadly, it wasn't easy for us at this case, but what we learned is Hirschhorn apparently solved this recurrence. So this type of recurrences were solved by Hirschhorn as a threefold sum. It's a huge sum, but all of these type of recurrences with the initial conditions 0 and 1 were solved. So why not use that? So I put the Hirschhorn sum here, and I'm just making a value list. So now let me look at the difference. I'm just going over it, brushing over it. The difference is 0, right? So now I can just show that Hirschhorn sum satisfies. I already know it's proven that Hirschhorn sum satisfies this recurrence. I can go back and back and back and prove that the product that I have is equal to the sum that is going to come from Hirschhorn, and the product that I have is the Borodin's theorem, which gives us this. So Hirschhorn had a threefold sum. I already got rid of one sum using the shift equation. So now a fourfold sum is equal to this product. And once you have decided, you can simplify it. Here is the simplification of it. Still not looking simple. It is a fourfold sum, including 1 q Pokemon, 3 q binomials, is equal to a product. If you're in Q series, you will see that this is a Bressu product that appears in the chain of Bressu identities. And I can easily say, yeah, maybe someone can simplify this sum. It's an exercise. Now, we have all this extensive literature of summing identities, all these hypergeometric identities. Maybe we can sum this summation and use some clever substitutions to reduce the number of sums here. And it's going to be equal to a product. But I tend to be, not say lazy, but I tend to be opportunistic. So why not try to experimentally find a simplification of that too? And that portion brings me to the last part about this package, that you can say, okay, I have all this data. I have all this data, like 10 of them, all the polynomials. Can you please try to fit something to this? And there are some parameters here, but I take my data, I pick my index to be n, I pick q, and there's a fit q representation, which searches for a closed form, which searches for a form that would fit the data that I have in q binomials, in q trinomials, in q tn trinomials, in q capital Tn trinomials, in q un trinomials, q vn trinomials, a lot of base functions, basically. And it just tries to fit the data that we give it using the first 5 data. First, let's say 2 values. And this 1, 0 is, in this list, I want to use all the 0 modulo, I want to use all these terms. A, 1, and plus 0. So if you want to use two more trees, you can just change them to 3 and 2, and then you will be jumping in your list. Because sometimes it might be helpful. Yeah. If you were to look at this using only the two values, so 1 and 2, if you want to fit those, this fit Q representation finds that you can do it with using these Q binomial plus 2 Q times that. Doesn't look bad. The coefficients don't go crazy, so you can try to do it with more values. Let's say try 5. The coefficient still doesn't look that crazy. So you get more terms. Of course you're going to get more terms. But the coefficients are not that crazy. So let's go 10. And now it looks promising. Because I always fit this polynomial set with Q binomials. And I always get either a single term with a Q binomial or two terms with a Q binomial. So if you can formulate that, maybe that's the solution. And that's it. This is the formulation of that. And the outside is how we pulled down stuff with the substitutions before. So now you have a simpler sum. Instead of a fourfold sum, you have a twofold sum. There's the sum outside and sum inside. Is turning into a product on the other side. And we found this experimentally, but proving that once you find the form is a piece of cake. Again, there are all these symbolic packages of risk, which was already at our disposal. That's why you didn't include that at all. That you can just put this term and say, can you find the returns for this? Bam, you will get the returns in a second. And that'll be it. And I think that should be it for my talk. So I hope you will use this qFunctions package, not to take anyone away from Maple, but Mathematica has a lot of good packages. Thank you for your time, and it's great to be here.